Hello there, and welcome back to The Sleepy Scientist, where curiosity meets comfort and science takes the gentle path toward understanding. I'm so glad you found your way here tonight. Whether you're settling into bed, curling up in your favorite chair, or simply looking for a moment of calm in what might have been a rather chaotic day. Tonight, we're embarking on a particularly fascinating journey through one of the most persistent questions in human history, one that might seem absurdly simple at first glance, but reveals layers of complexity that have captivated minds for thousands of years. We're going to explore a question that has sparked passionate debates, launched scientific expeditions, and even in our modern age of satellites and space travel, continues to intrigue a dedicated community of believers. Is the Earth really flat? Now, before we begin this gentle exploration, I want to acknowledge something rather beautiful about this question. At its heart, it represents something fundamentally human, our desire to understand the world through our own direct experience. When you step outside and look around, the Earth does appear remarkably flat, doesn't it? The horizon stretches in a seemingly straight line, water appears to lie level, and buildings don't seem to be tilting away from you, as they would if you were standing on the surface of a ball. These observations aren't foolish. They're the natural conclusions of careful, thoughtful people trying to make sense of their immediate surroundings. The story we're about to unfold together isn't really about proving or disproving anything. Instead, it's about the beautiful, sometimes messy, always human process of discovery. It's about how our ancestors looked up at the sky and out at the horizon, how they asked questions and sought answers, how they built upon each other's ideas and sometimes had to let go of beliefs that no longer served them. It's about the patient accumulation of evidence, the careful construction of understanding, and the remarkable journey from ancient wisdom to modern knowledge. Perhaps you've wondered about this yourself. Maybe you've stood on a beach and watched ships disappear, hull first over the horizon. Or perhaps you've flown in an airplane and noticed the subtle curve of the Earth's edge. Maybe you've heard passionate arguments from flat Earth believers and found yourself curious about their perspective, wondering how two groups of people can look at the same evidence and reach such different conclusions. Tonight, we'll trace this question from its ancient roots, when the shape of the Earth was a genuine mystery that occupied the greatest minds of their time, through the elegant experiments and observations that gradually revealed our planet's true nature, and finally to the modern resurgence of flat Earth beliefs in our digital age. We'll meet ancient Greek philosophers who calculated the Earth's circumference with startling accuracy using nothing but shadows and geometry, medieval scholars who never really believed the Earth was flat, despite popular misconceptions, and modern scientists who photographed our beautiful blue marble from space. But more than anything, we'll explore why this question matters, why it continues to captivate us, and what it reveals about the very human struggle to understand our place in the cosmos. We'll discover that the path to knowledge is rarely straight, that good intentions can sometimes lead us astray, and that the truth, when we finally glimpse it, is often more beautiful and more strange than anything we could have imagined. So settle in, let your breathing slow, and prepare for a journey that spans millennia. Whether this discussion helps you drift gently towards sleep, or keeps you delightfully awake with wonder, I hope you'll find something meaningful in our exploration together. Because the story of how we came to understand the shape of our world is really the story of how we came to understand ourselves. Curious, questioning beings spinning through space on a remarkable planet that we're only just beginning to truly comprehend. Are you ready? Let's begin this gentle voyage through time, across oceans, and into the very heart of human curiosity. The question of whether the Earth is flat may seem settled to most of us, but the journey to that understanding is anything but simple. And the story itself, well, that's where things get beautifully complicated. To understand why the question of the Earth's shape has persisted through history, we need to step back in time, far back, to an era when the world was a much smaller, more mysterious place. Imagine, if you will, living in ancient Mesopotamia, around 3000 BCE. Your entire world consists of the fertile valleys between the Tigris and Euphrates rivers, vast stretches of farmland that extend to distant mountains on one side and endless desert on the other. The earth beneath your feet feels solid, stable, fundamentally flat. The sky above appears as a great dome, with the sun, moon, and stars moving in predictable patterns across what seems to be a vast celestial ceiling. This is the world our ancestors inhabited. And from their perspective, the earth being flat wasn't a theory or a belief. It was simply an obvious fact based on direct observation. When you walked to the edge of your known world, the land didn't curve away beneath your feet. Water, when left undisturbed, settled into perfectly level surfaces. The horizon appeared as a straight line no matter which direction you faced. These weren't primitive misconceptions. They were rational conclusions drawn from the best available evidence. In ancient Egypt, the prevailing cosmology imagined the earth as a flat disk floating on a vast ocean of primordial waters. The sky goddess Nut arched her star-spangled body over the earth, supported at the cardinal points by mountains or pillars. The sun god Re traveled across this celestial dome during the day and through the underworld at night, explaining the cycle of day and night in a way that felt both logical and spiritually satisfying. This wasn't ignorance. It was a sophisticated attempt to explain complex observations within a framework that made sense of both the physical and spiritual aspects of existence. But even in these ancient times, careful observers began to notice things that didn't quite fit the flat earth model. Sailors, those brave souls who ventured beyond the sight of land, reported strange phenomena. Ships appeared to sink into the sea as they sailed away, disappearing hull first, while their sails remained visible for a time longer. When returning to port, the reverse happened. Sails appeared on the horizon before the body of the ship became visible. This wasn't magic. It was geometry, though the mathematical framework to understand it wouldn't develop for centuries. Astronomers, or more accurately, astronomer priests, who watched the skies for religious and agricultural purposes, noticed other peculiarities. During lunar eclipses, when the earth passed between the sun and moon, the shadow cast on the moon's surface was always circular, regardless of the time of night or season. They observed that certain stars visible in Egypt couldn't be seen when traveling south to Nubia, while new stars appeared that had been invisible from their northern homeland. The North Star, so reliable for navigation in northern regions, appeared lower and lower in the sky as one traveled south, and eventually disappeared entirely. These observations accumulated slowly, passed down through generations of scholars and seafarers, creating a growing body of evidence that challenged the simple flat earth model. But it would take the revolutionary thinking of ancient Greek philosophers to begin assembling these clues into a new understanding of our world's true shape. Around the 6th century BCE, as Greek civilization flourished and trade networks expanded across the Mediterranean, a remarkable intellectual revolution began. This was the era when human beings first began to systematically question the nature of reality, to seek natural rather than supernatural explanations for the phenomena they observed. It was during this period that the first recorded arguments for a spherical Earth emerged, not from religious revelation or ancient tradition, but from careful observation and logical reasoning. Pythagoras, the mathematician famous for his theorem about right triangles, was among the first Greek thinkers to suggest that the Earth might be spherical. His reasoning was based on what he observed in the heavens. The sun and moon appeared to be spherical objects, and he argued that the Earth, being a celestial body itself, should share this property. It was an elegant argument based on symmetry and harmony, concepts that were central to Pythagorean philosophy. But it was Aristotle, writing in the 4th century BCE, who presented the first systematic evidence-based argument for the Earth's spherical shape. In his work on the heavens, Aristotle laid out several lines of evidence that were remarkably sophisticated for their time. He pointed to the circular shadow that the Earth cast on the moon during lunar eclipses, noting that only a spherical object could cast a circular shadow from any angle. He described how travelers to the south could see stars that were invisible from Greece, while northern stars disappeared below the horizon, a phenomenon that made perfect sense if the Earth was curved, but was difficult to explain if it was flat. Aristotle also made an observation that anyone can verify today. As ships sail away from port, they don't simply become smaller until they disappear, as they would on a flat surface. Instead, They appear to sink into the sea with the hull disappearing first while the sails remain visible. This, he argued, was exactly what you would expect to see if the Earth's surface was curved. What's remarkable about these ancient Greek insights is not just their accuracy, but their methodology. These weren't wild guesses or mystical revelations. They were careful conclusions drawn from systematic observation and logical reasoning. The Greeks had discovered something profound that human reason applied carefully to empirical evidence could reveal truths about the world that weren't immediately apparent to casual observation. But perhaps the most astonishing achievement of ancient Greek science came from a brilliant scholar working in Alexandria around 240 BCE. Eratosthenes was the chief librarian at the famous Library of Alexandria, and he possessed something that made all the difference in the world: accurate, systematic observations from multiple locations. He had heard that in the city of Syene, far to the south of Alexandria, there was a deep well that became completely illuminated by the sun at noon on the summer solstice. The sun shone straight down the well, casting no shadow on its walls. Eratosthenes realized that this simple observation held the key to something extraordinary. If the earth was flat, the sun should cast no shadows anywhere at noon on the summer solstice. Its rays would hit the surface at the same angle everywhere. But if the earth was curved, the sun's rays would strike different locations at different angles, creating shadows of different lengths. On the summer solstice, Eratosthenes measured the shadow cast by a vertical stick in Alexandria at noon. He found that the shadow indicated the sun was about 7.2 degrees from directly overhead. Since 7.2 degrees is about 1/50th of a full circle, Eratosthenes reasoned that the distance between Alexandria and Syene must be about 1/50th of the Earth's total circumference. The distance between the two cities was approximately 800 kilometers, so Eratosthenes calculated that the Earth's circumference must be about 40,000 kilometers. Remarkably, this calculation, performed over 2,000 years ago using nothing but shadows and geometry, was accurate to within a few percent of the actual value we know today. It was one of the most brilliant scientific achievements in human history, and it provided conclusive proof that the Earth was not only spherical but also gave humanity its first accurate measurement of our planet's size. Yet despite these remarkable ancient insights, the knowledge of the Earth's spherical shape wasn't universal or immediate in its acceptance. Different cultures, working with different sets of observations and philosophical frameworks, continued to develop their own models of the world. The transition from flat Earth to spherical Earth thinking wasn't a simple linear progression. It was a complex cultural and intellectual evolution that unfolded differently in different parts of the world and took many centuries to complete. But here's where our story takes an intriguing turn, one that reveals just how complex the relationship between knowledge and belief can be. You might expect that after Eratosthenes' brilliant calculation and Aristotle's careful observations, the question of the Earth's shape would have been settled once and for all. The evidence was clear, the reasoning was sound, and the mathematical proof was elegant. Yet as centuries passed and civilizations rose and fell, something curious happened. The knowledge didn't spread evenly, and it certainly didn't stick everywhere it went. Let's follow the thread of this knowledge as it wound its way through history, sometimes blazing bright in the minds of scholars, and sometimes dimming to little more than a whisper passed between learned individuals. It's a journey that reveals just how fragile scientific understanding can be, and how easily even the most brilliant insights can be lost, distorted, or forgotten. After the golden age of Greek science, much of this astronomical knowledge was preserved and expanded upon by Roman scholars and administrators. The Romans, practical as always, were particularly interested in the spherical Earth model, because it had direct applications for navigation and map-making. Roman engineers and surveyors used spherical geometry in their work, and Roman traders navigating the Mediterranean relied on the understanding that the Earth was curved when planning their routes. But then something remarkable happened. As the Roman Empire began to fragment and transform, much of this scientific knowledge began a migration eastward. Islamic scholars in the expanding Muslim world encountered Greek scientific texts, translated them into Arabic, and not only preserved them but significantly expanded upon them. During Europe's medieval period, While many scientific traditions were dormant or reduced to simplified forms, Islamic astronomers were building observatories, calculating the Earth's circumference with even greater precision than Eratosthenes, and developing sophisticated mathematical models of our planet's shape and movement. Scholars like al-Biruni in the 11th century calculated the Earth's circumference using a method involving measuring angles from mountaintops, achieving accuracy that wouldn't be surpassed for centuries. Islamic geographers created detailed maps that assumed a spherical Earth, and Islamic navigators used spherical trigonometry to plan voyages across the Indian Ocean. The knowledge wasn't just preserved, it was actively developed and refined. Meanwhile, something interesting was happening in medieval Europe. Contrary to a persistent modern myth, educated Europeans during the Middle Ages didn't believe the Earth was flat. Medieval scholars, particularly those in monasteries and early universities, were well aware of the ancient Greek arguments for a spherical Earth. Thomas Aquinas, one of the most influential medieval philosophers, wrote extensively about the Earth's spherical shape. Dante's Divine Comedy, written in the early 14th century, describes a journey through a spherical Earth, from the northern hemisphere to the southern hemisphere. The myth that medieval Europeans believed in a flat Earth is largely a modern invention, created during the 19th century to support a narrative about the conflict between science and religion. In reality, the question that occupied medieval scholars wasn't whether the Earth was round, but whether there could be people living on the other side of it, and if so, what that meant for Christian theology. But here's where things get fascinating. While the intellectual understanding of the Earth's spherical shape persisted among scholars, the practical implications of this knowledge took much longer to fully realize. Even as learned individuals accepted that the Earth was round, the vastness of its size, correctly calculated by Eratosthenes, made the practical exploration of this spherical world seem almost impossible. Think about it. If you're a medieval European and someone tells you that the Earth is a sphere with a circumference of 40,000 kilometers, that's not inspiring. It's terrifying. It means that the known world, all of Europe and the Mediterranean and perhaps some vague knowledge of Asia and Africa, represents only a tiny fraction of the Earth's surface. It means there are vast, unknown expanses of ocean and land that no one has ever seen. It means the world is much, much larger and more mysterious than anyone had imagined. This is part of what made Christopher Columbus's proposal so controversial when he presented it to various European courts in the late 15th century. Columbus wasn't trying to prove that the Earth was round. Educated people already knew that. He was arguing that it was small enough that one could sail west from Europe and reach Asia before running out of supplies. Columbus had made a crucial error in his calculations, severely underestimating the Earth's circumference, but this error made his proposed voyage seem feasible rather than suicidal. When Columbus sailed west in 1492, he wasn't proving that the Earth was round. He was betting his life on the assumption that it was smaller than it actually was. The fact that he encountered the Americas instead of Asia probably saved his expedition from disaster, because if the Americas hadn't been there, Columbus and his crew would likely have perished in the vast Pacific Ocean long before reaching their intended destination. But Columbus's voyages did accomplish something crucial. They demonstrated that the theoretical knowledge of the Earth's spherical shape could have practical consequences. If the Earth was truly round, then it should be possible to reach any point on its surface by traveling in any direction, given sufficient time and resources. The age of exploration that followed was, in many ways, humanity's first large-scale experimental test of the spherical Earth model. As European explorers circumnavigated the globe, mapped new continents, and established trade routes that spanned the Earth, they weren't just discovering new lands, they were confirming, through direct experience, what ancient Greek mathematicians had deduced through pure reasoning over a millennium earlier. Each successful circumnavigation was another piece of evidence that the Earth was indeed a sphere, and each new map that accurately depicted the relationships between distant continents was a testament to the power of mathematical reasoning applied to careful observation. Yet, even as the practical evidence for a spherical Earth accumulated, pockets of flat Earth belief persisted in various forms. Some isolated communities, cut off from the broader intellectual currents of their time, maintained traditional cosmologies that depicted the Earth as flat. More significantly, the question of how to reconcile spherical Earth knowledge with various religious texts remained a source of debate and sometimes conflict. What's particularly interesting is how different cultures processed this transition differently. While European explorers were confirming the spherical Earth model through navigation, Chinese scholars had their own rich tradition of astronomical observation that had independently arrived at similar conclusions about the Earth's shape. Islamic astronomers continued to refine their measurements and calculations. Indigenous navigators in the Pacific had developed sophisticated wayfinding techniques that worked precisely because they understood the curved nature of the Earth's surface. The knowledge wasn't spreading uniformly, but it was spreading, carried by trade routes, scholarly exchanges, and the practical needs of navigation and exploration. Each successful ocean voyage, each accurate map, each precise astronomical observation added another layer of confirmation to what ancient Greek scholars had first proposed, that we live on the surface of a sphere spinning through space. As the centuries progressed and human knowledge expanded, you might think that the question of the Earth's shape would have been definitively settled. After all, by the 17th and 18th centuries, astronomers were using telescopes to observe other planets. Mathematicians were developing ever more sophisticated models of planetary motion, and explorers were mapping the globe with increasing accuracy. Yet, it was precisely during this period of remarkable scientific advancement that some of the most rigorous and beautiful proofs of the Earth's spherical shape were developed. Isaac Newton, the brilliant English mathematician and physicist who gave us the laws of motion and universal gravitation, made a startling prediction about our planet's shape in his masterwork, the Principia. Published in 1687, Newton argued that the Earth couldn't be a perfect sphere because it rotates on its axis once every 24 hours. Centrifugal force should cause it to bulge slightly at the equator and flatten slightly at the poles. In other words, the Earth should be an oblate spheroid, a sphere that's been gently squashed from top to bottom. This was a remarkable example of theoretical physics making a prediction that could be tested through careful measurement. If Newton was right, then the distance around the Earth measured at the equator should be slightly greater than the distance measured through the poles. The difference wouldn't be enormous. Newton calculated it at about 1 part in 230, but it should be measurable with sufficiently precise instruments. The French Academy of Sciences decided to test Newton's prediction through one of the most ambitious scientific expeditions in history. They organized 2 separate expeditions, one to Lapland, near the Arctic Circle, to measure the length of a degree of longitude in the far north, and another to Peru, near the equator, to make the same measurement in the tropics. If Newton was correct, a degree of longitude should be slightly longer near the poles than near the equator, because the Earth's surface curves more sharply in the flattened polar regions. The expeditions, carried out in the 1730s, were grueling affairs. The team in Lapland, led by Pierre-Louis Maupertuis, endured harsh Arctic conditions, battling extreme cold, difficult terrain and equipment failures. The team in Peru, led by Charles-Marie de la Condamine, faced different but equally formidable challenges: high altitude, tropical diseases, political instability, and the logistical nightmare of transporting delicate surveying equipment across the Andes Mountains. But the results were worth the hardship. When the measurements were finally compared, they confirmed Newton's prediction with remarkable accuracy. The Earth was indeed an oblate spheroid, slightly flattened at the poles and bulging at the equator, exactly as Newton's theory of gravitation had predicted. It was a triumph of theoretical physics and careful observation, demonstrating not only that the Earth was spherical, but revealing precise details about its shape that could never have been determined through casual observation. These geodetic expeditions marked the beginning of a new era in our understanding of the Earth's shape and size. Throughout the 18th and 19th centuries, scientists conducted increasingly sophisticated surveys, using improved instruments and mathematical techniques to map the Earth's surface with unprecedented precision. The Great Triangulation Surveys of India, the mapping of the American frontier, the careful measurement of the meridian arc through France. All of these projects contributed to our knowledge of the Earth's true dimensions and confirmed through thousands of independent measurements that we live on the surface of a slightly flattened sphere. But perhaps the most elegant and accessible demonstration of the Earth's spherical shape came from an unexpected source, the humble pendulum. In 1851, the French physicist Léon Foucault suspended a heavy weight from a long wire in the Panthéon in Paris and set it swinging. The pendulum, Foucault argued, should continue swinging in the same plane relative to the fixed stars, while the Earth rotated beneath it. To observers on Earth, this would make it appear as though the pendulum's plane of oscillation was slowly rotating. When Foucault's pendulum was set in motion, it behaved exactly as predicted. Over the course of a day, the plane of the pendulum's swing appeared to rotate slowly, completing one full revolution in about 32 hours. But of course, the pendulum wasn't really rotating. The Earth was rotating beneath it. Foucault's pendulum provided direct, observable proof that the Earth rotates on its axis, and by extension, that it must be a sphere rather than a flat surface. The beauty of Foucault's experiment was its simplicity and immediacy. Anyone could observe it and understand it. There was no need for complex calculations or specialized knowledge. You could literally watch the Earth rotate beneath your feet. Foucault pendulums were soon installed in museums and universities around the world, providing millions of people with direct, tangible evidence of our planet's rotation and spherical shape. Meanwhile, advances in astronomy were providing additional confirmation from an entirely different perspective. As telescopes improved and astronomical observations became more precise, it became clear that other planets in our solar system were spherical objects. Jupiter's moons, visible through a modest telescope, were obviously round, and they cast round shadows as they passed in front of their parent planet. Saturn's rings, a marvel visible through any decent telescope, made perfect sense if Saturn was a sphere, but would be inexplicable if planets were flat disks. The discovery of stellar aberration by the English astronomer James Bradley in the 1720s provided yet another line of evidence. Stellar aberration is a tiny shift in the apparent positions of stars caused by the Earth's motion around the Sun. It's analogous to the way raindrops appear to come at you at an angle when you're running, even though they're falling straight down. The fact that stellar aberration followed exactly the pattern predicted by the Earth's orbital motion provided compelling evidence that the Earth was indeed moving through space in the way that astronomical theory predicted. By the mid-19th century, the convergence of evidence from geodesy, astronomy, physics, and exploration had made the spherical Earth model essentially unassailable. Every careful measurement, every theoretical prediction, every observational test confirmed that we live on the surface of an oblate spheroid orbiting the Sun. The question seemed settled beyond any reasonable doubt. But then something unexpected happened. Just as the scientific evidence for a spherical Earth was reaching its most complete and convincing form, a movement emerged to challenge it. In 1849, an English writer named Samuel Shenton founded what would become the Flat Earth Society, dedicated to promoting the idea that the Earth was in fact a flat disk. This might seem like a historical curiosity, but it's actually quite significant. It marked the beginning of modern flat Earth belief as a conscious rejection of scientific consensus, rather than simply a holdover from pre-scientific thinking. The modern flat Earth movement was qualitatively different from ancient flat Earth cosmologies. Ancient peoples believed the Earth was flat because it was the best explanation available for their observations. Modern flat Earth believers, by contrast, had to actively reject an enormous body of scientific evidence and construct elaborate alternative explanations for phenomena that were easily explained by the spherical Earth model. Samuel Shenton, and later Daniel Shenton, who took over leadership of the Flat Earth Society, argued that the Earth was a flat disk with the Arctic at the center and Antarctica forming an ice wall around the perimeter. They claimed that what we call gravity was actually the result of the Earth accelerating upward through space, and that the apparent curvature observed by high-altitude flights and space missions was the result of optical illusions or deliberate deception. What's particularly interesting about modern flat Earth theory is how it represents a fundamental shift in the relationship between observation and explanation. While ancient flat Earth beliefs were based on direct observation that hadn't yet been extended or refined through scientific methods, modern flat Earth theory requires believers to distrust not only scientific instruments and calculations but their own potential observations. If you were to fly high enough, travel far enough, or simply look carefully enough at the right phenomena, you could verify the Earth's spherical shape for yourself. Modern flat Earth belief requires either avoiding such experiences or explaining them away as illusions or deceptions. This brings us to one of the most profound developments in the history of our understanding of Earth's shape, the space age. When humans first left the Earth's surface and looked back at our planet from space, they weren't conducting an experiment or testing a theory. They were simply seeing what had been predicted by mathematics and confirmed by centuries of careful observation. The first photographs of Earth from space, taken during the Apollo missions, didn't prove that the Earth was round so much as they provided the most direct visceral confirmation of what science had already established. The image of Earth from space, a blue marble suspended in the black void, clearly and unmistakably spherical, became one of the most powerful and iconic images of the 20th century. It wasn't just a pretty picture. It was the culmination of thousands of years of human curiosity, careful observation, and scientific reasoning. In a single photograph, you could see the result of all those ancient Greek calculations, all those surveying expeditions, all those astronomical observations, all those theoretical predictions. There was the Earth, exactly as science had said it would be, a beautiful, fragile sphere floating in the cosmos. Yet even the direct photographic evidence from space hasn't ended flat Earth belief. In our modern digital age, flat Earth communities have found new life online, where believers can connect with each other, share alternative explanations for scientific evidence, and create elaborate theories about government conspiracies and faked space missions. The Internet, which has democratized access to scientific information in unprecedented ways, has also enabled the spread of scientific misinformation and conspiracy theories. This presents us with a fascinating paradox. We live in an age when the evidence for the Earth's spherical shape is more abundant, more accessible, and more compelling than ever before, yet flat Earth belief persists, and in some ways has grown stronger. This suggests that the question of the Earth's shape has evolved beyond simple matters of evidence and observation to touch on deeper issues of trust, authority, and the nature of knowledge itself. Modern flat Earth believers often frame their position not just as a disagreement about geography, but as a broader skepticism about scientific institutions, government agencies, and other sources of authority. They argue that the spherical Earth model is part of a broader conspiracy to deceive the public, and they present flat Earth belief as a form of independent thinking and resistance to authority. As we've seen throughout this journey, the question of the Earth's shape has never been simply about geometry or geography. It's always been deeply intertwined with larger questions about how we know what we know, whom we trust to tell us about the world, and what it means to live in a universe that often defies our immediate intuitions. And perhaps nowhere is this more evident than in the remarkable ways that modern technology has both strengthened the evidence for our planet's spherical shape and, paradoxically, enabled new forms of skepticism about that very same evidence. Consider for a moment the array of modern tools and technologies that continuously confirm the Earth's spherical shape. Global Positioning System satellites, which most of us carry in our pockets in the form of smartphones, work only because they account for the Earth's curvature and rotation. The GPS network consists of at least 24 satellites orbiting the Earth at an altitude of about 20,000 kilometers, and each satellite contains atomic clocks that must be adjusted for relativistic effects caused by their motion and the Earth's gravitational field. The entire system is based on the assumption that the Earth is an oblate spheroid, and it works with such precision that it can locate your position to within a few meters anywhere on the planet. Weather satellites continuously photograph the Earth from space, providing images that clearly show our planet's spherical shape, the curvature of the horizon, and the way weather systems wrap around the globe. Communication satellites enable global telecommunications by relaying signals around the Earth's curvature, something that would be impossible if the Earth were flat. The International Space Station orbits the Earth every 90 minutes, and astronauts aboard it regularly photograph and film the Earth's surface, documenting its spherical shape from every possible angle. But perhaps the most compelling modern evidence comes from an unexpected source. Ordinary people with access to relatively simple technology, high-altitude balloons equipped with cameras regularly reach altitudes of 30 kilometers or more, high enough to clearly see the Earth's curvature. These flights are conducted by schools, amateur scientists, and citizen researchers, and they consistently produce images that show the Earth's curved horizon. Anyone with a few $100s and some basic technical knowledge can conduct their own high-altitude balloon flight and see the Earth's curvature for themselves. Commercial aviation provides another accessible form of evidence. Long-distance flights follow great circle routes, the shortest path between 2 points on a sphere, rather than straight lines as they would appear on a flat map. A flight from New York to Tokyo, for example, follows a path that takes it far to the north, over Alaska and the Arctic, because that's the shortest route on a spherical Earth. These flight paths would make no sense if the Earth were flat, but they're the most efficient routes on a sphere. The internet age has also made it possible for anyone to access real-time data from thousands of scientific instruments around the world. Seismometers detect earthquakes and measure how seismic waves travel through the Earth's interior, providing detailed information about our planet's internal structure that confirms it's a solid sphere with a liquid core. Tidal gauges around the world measure the rise and fall of ocean levels caused by the gravitational pull of the moon and sun, demonstrating how these celestial bodies interact with our spherical planet. Amateur astronomers, with modest telescopes, can observe the same phenomena that convinced ancient Greek philosophers of the Earth's spherical shape. They can watch lunar eclipses and see the Earth's round shadow crossing the moon's surface. They can observe how the constellation of stars visible from their location changes as they travel north or south. They can see how ships disappear hull first over the horizon, exactly as Aristotle described over 2,000 years ago. Yet, despite this overwhelming abundance of evidence, flat Earth belief has not only persisted, but has experienced a remarkable resurgence in the digital age. Online communities dedicated to flat Earth theory have grown substantially, and flat Earth conferences now attract hundreds of attendees. YouTube videos promoting flat Earth ideas have garnered millions of views, and social media platforms have become venues for spirited debates about the shape of our planet. This modern flat Earth movement presents a fascinating case study in how people process information in the digital age. Flat Earth believers have developed sophisticated explanations for virtually every piece of evidence that supports the spherical Earth model. They argue that satellite images are fabricated, that GPS works through ground-based systems rather than satellites, that the apparent curvature seen from high altitudes is an optical illusion caused by fisheye camera lenses, and that space agencies around the world are involved in a massive conspiracy to hide the truth about the Earth's flat shape. The movement has also developed its own alternative model of the Earth and cosmos. In the most common flat Earth model, the Earth is depicted as a flat disk with the North Pole at the center, and Antarctica forming an ice wall around the perimeter. The Sun and Moon are portrayed as local objects, perhaps 50 kilometers in diameter and 5,000 kilometers above the Earth's surface, moving in spirals to create the illusion of seasons and day-night cycles. Gravity is explained as the result of the Earth accelerating upward through space, and the other planets and stars are described as lights in the sky rather than distant spherical worlds. What's particularly intriguing about modern flat Earth theory is how it demonstrates the power of motivated reasoning, the human tendency to seek out information that confirms our existing beliefs, and to dismiss or rationalize away information that challenges them. Flat Earth believers often describe their position as the result of independent research and critical thinking. This raises profound questions about the nature of evidence, expertise, and knowledge in our modern world. In principle, we live in an age of unprecedented access to information, Anyone with an internet connection can access scientific papers, satellite imagery, educational resources, and real-time data from instruments around the world. Yet this same technology that provides access to accurate information also enables the rapid spread of misinformation and the formation of communities organized around shared misconceptions. The flat Earth phenomenon also reflects broader tensions in contemporary society about the role of expertise and authority. Many flat Earth believers express deep skepticism, not just about the shape of the Earth, but about scientific institutions, government agencies, and other traditional sources of authority. They frame their beliefs as a form of rebellion against a system they perceive as dishonest or controlling, and they view their rejection of mainstream science as evidence of their independence and critical thinking abilities. This presents a particular challenge for science education and public understanding of science. Traditional approaches to science communication often assume that providing more evidence and better explanations will convince people to accept scientific conclusions, but the Flat Earth movement demonstrates that this assumption isn't always correct. When people's fundamental beliefs about the nature of knowledge and authority are in conflict with scientific evidence, simply providing more evidence may not be sufficient to change their minds. The persistence of flat Earth belief in the modern world also highlights the importance of scientific literacy and critical thinking skills. While it's true that most people will never need to personally verify that the Earth is spherical, the ability to evaluate evidence, understand the scientific method, and distinguish between reliable and unreliable sources of information is crucial for making informed decisions about a wide range of issues that do directly affect our lives. Perhaps most importantly, the flat Earth phenomenon reminds us that science is not just a collection of facts about the world, but a way of thinking about the world. It's a method for distinguishing between what we know and what we merely believe, between what the evidence supports and what we might wish were true. The scientific understanding of the Earth's shape didn't emerge overnight, and it wasn't the result of a single brilliant insight. It was the product of centuries of careful observation, rigorous reasoning, honest questioning, and the willingness to change our minds when the evidence demanded it. The story of how we came to understand the Earth's shape is, in many ways, the story of how science works at its best. It shows us how human curiosity and ingenuity can overcome the limitations of our immediate experience, how careful reasoning can reveal truths that aren't immediately obvious, and how the patient accumulation